In this video, we cover two things: molarity and how that captures the concentration of a solution. So it's all going to be about solutions in this chapter, where we have some solute A in some sort of solvent that is, I guess, like water would be the common type, that's more abundant. So some solute in solvent gives us a concentration. And we capture that quantitatively using molarity. So we'll talk about that, and we'll also just talk about solution properties. Colligative properties are part of solutions. We need to understand how to capture then quantitatively solutions and how to think of them qualitatively. So a general rule qualitatively is that like dissolves like. So if we want to know what solvent is best for a solute, make sure that these are alike. Whether it be they can both undergo hydrogen bonding, or maybe they're both nonpolar, so both being nonpolar, nonpolar likes nonpolar, polar likes polar. It's not always true, but it's a good functional rule to start with. Like dissolves like. Molarity. So molarity is a way of capturing how much of the solute did you get into the solvent. We do it by saying we want to know the moles of solute per the volume or liters of solution. Now I'm going to put that here, of solution. So we're not saying of solvent, we're saying liters of solution. So we would measure some amount that this solution measures up to, not how much solvent we added at the beginning. This is the way we talk about molarity: moles of solute versus liters of solution. You'll want to remember that, calculation. It's moles of solute over liters of solution. We can use that for making determinations on what the molarity is of a dilution. So this is really an equation for a dilution, where we take some solution of a certain molarity and a certain volume, and we add water. And if we add water, pure water, then the calculation will be M1V1 is equal to M2 molarity times V2, the final volume of that new solution that we've diluted. We'll talk about osmotic pressure. We'll talk about vapor pressure. This will be in the next video, and boiling point and freezing point depression and boiling point elevation. Some things that are due to colligative properties. These are all based on osmotic, vapor pressure, properties of solutions we call colligative properties. So that's going to be kind of the focus for the next video. So you know from our discussions of water and how it interacts with ions that we make solvent cages. So we have the hydrogens from water here, which are partially positive, interacting with the full negative to give us sort of an ion-dipole interaction, where there's a solvent cage, a shell, around the chloride. And we reverse the orientation when it comes to positive charge, because the oxygens from water want to be around the sodium. And so we really have in solution all these shells where these water molecules that are around the ions are kind of locked in, and they're tumbling and bubbling through the solution that we might have here. So you can see this sort of orientation. Not all the water is going to be oriented. There's going to be some in the gaps or in the spaces between these shells, but that's what's happening around the ions. We make shells. Remember that many of the molecular compounds containing carbon are only slightly soluble in water, or insoluble. They don't do this. Salts really are what we see solvated very well in water. Organic compounds, or what we call molecular compounds containing carbon, are not going to be very soluble in water. Now, if we have a salt, so if we have some salt, and it dissolves well in water, we always have then an electrolyte. That salt has made an electrolyte. So what do we mean, electrolyte? Well, we mean ions that can get jiggy. They can move around. They give us electrolytic behavior. So what is a strong electrolyte? It's where you have a lot of ions getting jiggy with it. A lot of ions dissolved, cations and anions in water. And here's how it happens. Electrolytic behavior. We can take and measure electrolytic behavior by having an alternating current, where we have this, let's say, positive pole, and this is a negative pole, but you turn another 20 thousandths of a second past this point in time, the pole will change, and this will become positive, and this will become negative. So we're going to illustrate that over here. We're going to say, hey, this pole was positive for 1/20,000th of a second, and then some time goes by, 1/20,000th of a second, and it alternates. So it has this negative pole now and this positive pole. And that's exactly what's happening in your outlets when you plug in your plug for charging your phone. This pole will be negative and this pole will be positive, but just a 20,000th of a second later, it'll go from being negative to being positive, and this will be going from positive to negative. You have an alternating current that you're using to maybe power your computer or turn on a light bulb, whatever. So that's kind of what we're going to use here. But instead of having electrons flowing through the solution, we're going to have ions moving in response to these charges, and that still allows for a current. If ions, we'll say these ones in red here that are at the very top row, are going to move, they're going to get jiggy and move towards the positive. And the ones that are blue, just below it in the second layer, are going to move to the negative. And by doing that, it allows electrons to flow, because if I'm allowing positives to move over, I can start putting more and more charge onto these poles. As the negatives move over, more electrons can move over here as positives move over. So you have, in the solution, you have ions moving. But in another 20,000ths of a second, we're going to have everything change. Those ions that were going to the left now are going to the right, because we've changed the pole. We've made this side, which was positive, go to negative. And so those ions will start just jiggling back and forth. They kind of respond to this alternating current that you're applying. We'll talk about that more in class. But that's the basis for electrolytic behavior of salt solutions. So we can have types of electrolytes that are really, really strong. The ones that are strong are salts that are highly soluble in water. But let's say we take and put a polar compound like acetone or acetic acid. I should draw a bigger picture. We can have a compound that's organic. It has, as you can see, one OH group for hydrogen bonding, but it has this part full of carbons, and this would be a not non-electrolyte. This would be a weak electrolyte. Put it over here, because it's not that it can't make ions at all. It can make, if we take it from this state to a negative charge on this oxygen, and we have a proton generated, and we only get this like 1 in every million, or sorry, 1 in every 100,000 does this, but it takes it from being not an electrolyte with no charge. You have to have charge. That's why salts like NaCl would be the best. That's why it's a strong electrolyte, because NaCl dissociates into negative and positives that can get jiggy with it. This acetic acid can, every 1 in a million, be in this state. Well, that's a negative on this structure, and that's a positive, so they can start getting jiggy with it. But not all of them do that. Not all of them go to ions. Now, in this case, if we take, let me give you an example of this one. If we take ethane, which is just CH3CH3 bonded together, that has no polarity. It's going to stay together in solution. Or sugar could be another one that we could put in there. Anything that doesn't ionize is a non-electrolyte. Let me say it again. Anything that does not ionize is a non-electrolyte. All right, we better get to molarity, and we'll stop there. We said it's moles of solute over moles of solution. That's what molarity is. We can have a solution, and these balls represent, let's say, 1 mole of the solute. Each ball represents 1 mole of the solute. So you can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we'll say it's like 17 molarity if this was a 1 liter solution. 1 liter, 17 moles, would say it's 17 molarity. So if we had 17 molarity as our, and we had our volume as 1 liter, if we add, let's say we add 1 liter of water, of pure water, is added to that solution, that's 17 moles. Well, how many moles of the solute do you still have over here if you added pure water? How many balls, you might say? it still should be 17. So if I had 17 turquoise balls over here, I should still have 17 here. That's the basis for this calculation, is moles equals moles, because molarity times volume is going to leave you with moles. So 17 times 1 is 17. But if we take and we know we add 1 liter, then our molarity should change. Our molarity is the moles per liter. So let's just figure out what M final would be. M final would be that 17 moles, 17 of these balls representing 1 mole each, divided by 2. So that would be, if I can do this, 8.5 molarity. So we'd say that is equal to 8.5 molarity. But remember what we did to the volume. We added 1 liter, so it went from 1 liter. We added 1 liter of pure water, so that's 2 liters. And so we're still going to get 17. Because the units you're left with are moles, and you can't lose moles if you add pure water. If there were 17 balls here, there's still 17 balls here. It's still going to be then 17 moles, 17 balls equals 17 balls. And that's all this really does. It's just take molarity times volume, which is equal to moles, must be equal to the new molarity times the new volume, because the moles don't disappear. We'll use this equation in class some more. Let's finish with this problem. Let's say you have a 10 mil of a 6 molar solution. 1, 2, 3, 4, 5, 6. We have 6 moles represented by those balls in some solution, 10 mils. Now let's say we dilute it to 20 mils. So we doubled the volume. What is the new molarity? Well, we're going to use that M1 V1 equals M2 V2 calculation. And we know the molarity is 6. I'm going to just leave the units off. And we have mils here. So we better change this to liters. So we know that's 0.01 liters, because we know we move the decimal point 3 places, 1, 2, and the third spot in front of the 0 in front of the 1. So we can have 6 times 0.01. And we want to know what the new molarity is, so I'm going to leave that as just M2. But we know the new volume is not 20 mils. We know if we move the decimal point 1, 2, 3, we have 0.02 liters. So what I can do then is just take my calculator and divide 6 times 0.01 by the 0.02. So divide that 0.02. And we get then 3. Our new molarity is 3. 3 big M. So we left with the unit big M. The new molarity would be 3 molarity. Let me put it up. The new molarity would be 3 molarity. Now this question is a really good follow-up question. If each ball represents a mole of solute, how many balls do you have after dilution? That was the last slide. 1, 2, 3, 4, 5, 6 balls. If we add pure water, there's still just going to be 6 balls, or 6 moles, we said, of our solute. All right, for sake of time, we'll stop there and work on this one in class. Number of moles of H2SO4 in 2 liters of a 4 molar solution. So molarity, to solve this one, we need to remember is equal to moles over liters. And I think with that, you can just plug in, because they tell you that you have a certain molarity. You can plug that in here, and you have a certain liter, and then you can just isolate moles. We'll do that in class, but I hope this video helps get us started on this discussion of not just what solutions are, but how we quantify it using molarity. Thanks.